Right, hey everyone. So this is chapter 2, part 2. Today we're going to be looking at chapter 2, sections 2.5 through 2.8, dealing with atomic structure, or excuse me, electronic configuration, electrons, valence electrons, periodic table trends, which have a lot to do with how the electrons are arranged, um, and Lewis dot structures. Okay, so all of this is kind of related to each other. So we'll just start with the electron, go back and kind of look at what it is and where they're located, and then we'll start talking about how we describe them and what that means for chemistry. Electrons have everything to do with chemical reactions, right? We said that we don't really change atoms, okay? You don't take protons and neutrons off atoms and make other elements, right? Once an element is an element, and that's pretty much what it's always going to be. Okay, there are a few cases where that's not true, but usually it has to do with nuclear fusion or some kind of high energy thing like that that most people will not deal with in their lifetime. Um, so with that being said, let's kind of go back and look at, well, first let me show you what we have on Cougar View. Okay, so where is Cougar View? This is Cougar View. So back on your content, chapter 2, you'll see that I posted some more videos. These are supplemental, not required. They're here in case you get hung up on anything about a certain topic. You can go back in and look at electron configuration, periodic table trends, valence electrons, Lewis dot structures, and they're all different teachers or different ways of showing the material that might kind of strike a chord with you, right? As I said, everybody learns differently, so I try to provide as many resources as possible. So here you have supplemental videos. We also have the PowerPoint from this chapter straight from the book. So we'll kind of go through that. I think I'll also flip back and forth to the text to make sure we're not missing anything. But today we're getting started on section 2.5, electronic configuration. And before we get into that, I want to kind of go over what we know about electrons so far, right? So we said that the atom consists of a nucleus, right, with protons and neutrons in here. And I'm not going to try to write anything, so just kind of follow along, pay attention. I'm working on getting my laptops ready, but I haven't got it synced up with my online broadcasting system. Short story long, I'm not quite there yet. I will have it ready by the time we start getting into the math and everything, because I want to be able to work problems for you. Also, if you get hung up, let me go back to this just for a second. If you get hung up on Alex, okay, if there's any problems on Alex that you can't get through or you don't understand the way the program is, you can obviously email me. So I've extended some assignments just to make sure you're able to get in there. You don't just because you completed a section does not mean you mastered it. Okay, so pay attention to what the labels on Alex are telling you. If it says um, go to objectives or something like that, and you'll see some tabs on the bottom that say uh, learned, mastered, review, stuff like that. So that's where you can see exactly which topics you haven't completed fully yet. Okay, so just because you get through a topic doesn't mean you've mastered it, and it might not give you full credit for the whole section. So you have to go into the ones that say learned, click on that, and then try to go through and master those. Let me see if I can pull up one of the Alex programs and just kind of show you what I'm talking about. Alex, let me see. Where is it? Where is it? Can y'all see that? Okay. Let me go to student view. And I think I've mastered. No, I haven't learned everything. Okay, so let me click on 2B. So this is the section we're working on now. Let me find out where that tab is. Assignments. Okay, so this is where you'll kind of see your grade, right? The progress on the right, and it'll tell you how many topics completed. Um, Let me say I'm going to click on 2B, and it takes me right into that. So none of these are mastered. Let me see. Now for the way that I was looking at it, oh, here it is. So if you click on that percentage, let me go back and show you that one more time. So I'm going to click on the percentage of my progress for whichever assignment, and you'll see here it has ready to learn, learned, mastered. All right. So a lot of you are learning these topics, but you're not mastering them. So it's not giving you full credit for the topic, right? And so that's how you get through with everything. And it says 8 out of 11 completed. It's because you've learned some, but not mastered them. So whenever it says you've learned something, you can click on there. You should be able to open back up that part of the assignment. Let me see how I do that. S block, nope, nope, nope. I guess that's when I would have to go to assignments and then click on 2B there, and it will take me to whatever I'm missing. Okay? Then also, if you still haven't completed everything at a certain point, I'm going to click on the percentage again and bring up that other one. Locked. Let's go to an assignment. Excuse me, an assignment that I've already done. Assignments, closed. Let's go 64. And I guess I'm not keeping up with it like y'all are with mine. So I just kind of go in here and do a few, and it doesn't. I guess they're closing me out. So let me know if you get closed out. I might can go back in there and extend it. In fact, I think I did extend most of these for everybody that hadn't done something or emailed me while I was on vacation. So go back in and look at your Alex, see what you've learned, what you've mastered, and you can try to complete some more of those. And I remember there being a review section if it's not closed, which mine is closed right now. Where it says locked here, there'll be a review. And let me see if I can click on this and do that. So there's a review in this tab right here, and it kind of takes you over the things that you've already worked on, but you can keep adding points to those topics if it's not 100%, right? So, just if you have any questions with this, you can email me, include a screenshot of the problem you're working on, and I can use those when I go back and do the midterm review, right? And I work some Alex problems, kind of show you where most people went wrong, or explain it in terms of the Alex program. A lot of y'all are having problems just with the Alex program, not necessarily the content, right? So, my first time on Alex this semester. I'm working with it, learning same as you are, but we'll figure it out. So just if you have any questions about that, you can email me. I've extended a lot of the assignments so that you can go back in and keep working on it. All right? Because I think it locks you out after a certain point. All right, so now that we are done with that, let's go ahead and get into today's chapter. So remember we talked about electrons in the last lecture. We were looking at the nucleus, which consists of protons and neutrons, and then the electrons deposit on the outer, we called it an electron cloud. All right, but there's a lot of different names that you'll see for it. Orbit, orbital, energy level, right? Electron shell, We like to call it a shell, but it kind of makes that wall like we were talking about with a fan. When they move, everything moves so fast, nothing can get in there, right? It essentially builds like a wall for the atom because these electrons are moving around this outer shell so quickly, right? So I got electrons on here and here like that, all right? So that's where the electrons are. The electrons are on a outer shell orbiting around the nucleus, okay? And how close they are to the nucleus will determine how much energy they have. So it just counts the shells we call energy levels, principal energy levels, and they are designated with the letter N. Okay, so N equals 1, that would be the first energy level. N equals 2, that would be the second energy level, so on and so forth. And then electrons that are closer to the nucleus are lower in energy than those that are further away. So you have multiple shells that stack up around the atom like this. Sorry about the drawing. And then, so electrons on this outer shell are going to be higher in energy than those on this inside, this first energy level. Okay, so just for simplicity, I'll say that this is energy level 1, that's energy level 2, this is energy level 3. Okay, so the ones on level 3 are going to be way higher in energy than ones on level 1 or even on ones in level 2. So when electrons get deposited, they get deposited from the inside out, right? I'll fill up this first shell, then the next one that comes in will go to that second shell until the whole second shell has been filled, and then more electrons come in, it'll be on that third shell. So it'll keep stacking up and getting further and further away from the nucleus as you get more electrons. And we're going to talk about that. That's what we call electron configuration, right? Where are my electrons and how do I name them? Because I need to be able to identify each individual electron. And the reason that is because electrons have a lot to do with chemical reactions. In fact, everything. We said that atoms don't really change into other atoms. They just lose neutrons or electrons, gain or lose neutrons and electrons until it fulfills its purpose. Its lowest energy is how we like to say it. So atoms don't change. The only thing that really changes is electrons. Okay? I mean, we looked at isotopes and there are different isotopes, but when we're reacting atoms with each other, we're talking about the interactions of electrons. And so those are the most important to understand when we're talking about chemical reactions and understanding what can happen and what cannot happen when it comes to chemistry. Okay? Go back to the PowerPoint. So we said that electrons in lower numbered shells are closer to the nucleus and lower in energy. Shells with large numbers are farther from the nucleus, and they also hold more electrons. So that makes sense, right? If I look at this, see how number 1 is a very small, tight circle? So it can only hold 2 electrons. I can only get 2 electrons on that first energy level. All right. Then the next one is a little bigger. I can hold like 6 electrons on that next energy level, so on and so forth. And we'll have you'll see here a dedicated number for how many electrons can get held on each level. As it gets bigger, as it gets further away from the nucleus, the orbit gets bigger and bigger and bigger, and therefore I can fit more and more electrons. Okay, so these are set numbers of electrons that can get filled in for each energy level. Okay, and that N value will tell you which energy level it is on. Now, these shells are also divided into what we call subshells. So I'm going to come back over here to my drawing, and I'm going to put add another little part to it. Okay? So we said we have the nucleus here. Let me fill that in. We have an energy level here, so this will be 1s, and I can only put 2 electrons there, right? Oh my gosh, that's ugly. Okay, now the next one that comes will be another s. So remember, s can only hold 2 electrons. I can still only put 2 electrons here. And then another one that will be 2p. Okay, so let me do 2, 2, 6. I can hold 6 electrons on this p shell. Alright, so a couple confusing things about this that I'm going to address right now before we go any further. That kind of, I can imagine a lot of you are asking questions. Alright, so let me finish drawing this, and I'll go back and forth to the PowerPoint to explain. Alright, so we said that the energy levels, shell 1, energy level 1 can only hold 2 electrons. So this is the 1s that you see there, okay? 1s2. I got 2 electrons on the number 1, and that's all that I can fit. Then I go to energy level 2, and that's how come I put this 2 up there right here for 2s. That means electron energy level 2, principal energy level 2. All right, but now it says here that I can get 8 electrons on energy level 2, right? But you see that I've only put 2 on the s subshell. So the electron shells are divided into subshells as well. And you'll see here that an electron subshell has a different number of orbital. All right, we'll talk about an orbital here in a minute. Orbital is a region of space where the probability of finding an electron is high. Okay, that just means it's a ring, essentially. It's a pattern of rotation that we know an orbit around the nucleus. All right, they have 4 different subshells, S, P, D, F, and each subshell can hold a different number of electrons, but it's the same concept. So I can fit 2 electrons in every orbital, so 3 orbitals means I can hold 6 electrons, right? And that's what you see here on this diagram, right? I've created the second orbital for the the p orbital for the second energy level. All right, if I add all of the electrons up from that energy level, 2, right, 2, 2, I have 2 from the s subshell, and I have 6 from the p subshell, so that means energy level 2 has a total of 8 electrons. Okay, N2 has 8 electrons. And that follows with what we were saying about increasing energy level. As I get further away, I can hold more electrons, but we also divide them up based on how the electrons get deposited into what we call orbitals. All right, so I know this is a little tricky. We usually don't do this early in the semester. I like to look at other things, but either way, we're in it now. The orbitals is going to be one of the hardest concepts to understand. So I'm going to kind of look at that real quick. When they say the highest probability of finding an electron, so we say that the electrons move kind of like a fan blade. Let me just pull myself up for a second. Electrons kind of move like a fan blade, going round and round so fast that you can't see exactly where they are. All right, we don't know exactly where they are. We like to say that about electrons. You can never know exactly what point the electron's in because it's constantly moving so fast. All right, and it creates that cloud because it's moving so fast. It's not really a solid object. Think about like when you're watching a fan turn really fast. Kind of looks like it might be moving slow, but if you were to stick your hand in there, you get pop real quick no matter where the fan is in the rotation. So that's kind of how electrons work. They're moving so fast that we can't really see where they're at. And what they end up making are these little electron clouds. Okay, so notice that the S is just round. Okay, it's just two electrons going round and round and round in opposite directions, and they form this little ball, this little cloud, and that's how come the S orbital looks like a circle. Now for the P orbital, it moves a little different. It does like this, right? Oscillates, boom, 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 real fast. Okay, and so it ends up making that little shape that you see there with the two kind of ends on it, right? And now, so I got one electron going like this, I got another one coming like this, both of them intersecting and crossing and making this cloud, but there's 6 of them doing them on different planes. Okay, so while I got one coming back and forth like this, I got one coming up and down like this real fast, and then another one kind of cross angled like this, right? So let me get something to kind of orient with, right? So one of the p orbitals, let's say this is the atom. Let me get one that I can put something on both sides. Which there isn't much of that. Does that one work? Nope. I guess I don't have anything with opposite ends. Okay, so imagine this is like my plane or whatever. One atom will come down and up like that. Another one, excuse me, electron. These are electrons moving, right? One electron is on a path up and down. Another electron is on a path right to left. And then the third for the p orbitals is kind of diagonal, cross like this. Bang, 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 bang. All right, so that's how come you see 3 different orbitals for the p subshell, and it gets even more complicated when you start talking about the D and F subshell. But I don't think they're going to go into that, so I just wanted to kind of lightly touch on the orbital concept. It's one of the more tougher concepts in chemistry, and especially like for organic chemists and stuff, it gets to be very important, but I don't think we're going to use it that much. It's just an idea about how electrons are filled, and so it's good to know, but I don't think you'll have to know much about it, right? Just know that when electrons get in a certain subshell, they rotate in a certain manner. All right. The S is a small tight circle, boom, boom, boom. The P kind of does an oscillation like this. D gets even wilder. It comes up here, does a little circle, comes down here, and can go in multiple different dimensions. So for electron configuration, these are the rules to how you kind of fill out your electron configurations. You'll see from my paint program, let me go back to that paint. That's essentially what I was doing here with the 1s, 2s, 2p. So that is a electron configuration kind of indicating which spot of the periodic table I'm at, right? And as we get to the periodic table, you'll see that the reason it's arranged the way that it is to account for these different energy levels, okay? So I'm going to skip down just a little bit till it shows me the periodic table, okay? So remember, we've separated everything into these groups, and one of the reasons behind how they're separated are these subshells, these electron energy levels. Remember, I said the S can only hold 2 electrons. So all of these atoms from the first 2 rows, their electrons are on the S orbital, all right? And once I fill those up, I move over here to other energy levels. So I'll always fill in those S's first. Let's say I'm on period 2 here. Once I get over here to groups 3 through 8, I'm putting electrons in on the p orbital, right? And so that's how you see here is a electron configuration for Z equals 6. That would be what, right? 1, 2, 3, 4, 5, 6, right about here. Okay, I think that is carbon, I believe. Okay, and so just to count again, 1, 2, 3, 4, 5, 6 electrons. Remember, if it's neutral, that means 6 protons too. So it'll be atomic number 6. 1, 2, 3, 4, 5, 6. Yes, that's carbon. All right, and it'll fill out the electrons in this fashion. So you have rules. Uh, you have to fill in one at a time until the boxes are filled. Then you come back and do your opposite direction. Uh, Orbitals are filled in increasing energy, so you fill in the ones before the twos, and then there's a slight kind of hiccup, we'll call it, when you get to the transition metals, row 4, excuse me, right here. So see here that after I get to 4s, I go to 3d and then back up to 4p. Okay, so the D's are always one energy level behind, and we won't get into why that is, but 3D comes after 4S, and you'll get to play with this some. And then also the F's are one behind, but I'm not sure if you'll have to actually do any of those. So watch the video on Cougar View about electron configuration, and he'll kind of go into how you place all of these. I don't know that you'll actually do orbital notation, which is where you do the arrows up and down. I don't remember doing it until I was in organics. So if that's one of the objectives, I may look at that and get that removed. But anyway, so when you go to fill out your electron configurations, let's back up and just reiterate a few major points, right? Let me pull up a periodic table. Periodic table. Okay. So, just to kind of crash course it, hydrogen has one proton because it's the atomic number 1. So if it has one proton and it's a neutral hydrogen, it has to have one electron. When I fill out my orbital notation or my electron configuration, I would just put 1s1 for how many electrons are in the s orbital. Okay, for helium it would be 1s2. Okay, because I have 2 in the s orbital. Now once I come down to lithium, it becomes 2s. And then when I get over to boron, 2p. Boron would end, its electron configuration would end in 2p1 because I have one electron in this p orbital. All right. Carbon would have 2, and that's what we saw. Carbon was the one that we saw on your PowerPoint, right? This is carbon right here, Z equals 6. 6 electrons most likely means 6 protons. So 6 protons is the atomic number 6. If I look at the periodic table, carbon is number 6. All right. So, and you can keep on going. So just kind of an example. I'll work an example here. Let me clear this off. Select, clear, select, clear, pen. All right, so let me choose one a little more difficult. Let's say down in the d orbitals. So the d orbitals, let's say we're going to do chromium. Okay, so chromium is atomic number 24. If I have a neutral atom, I'm going to have 24 electrons as well. So I need to fill out my electron configuration to where I get 24 electrons. All right. So now without looking at the periodic table or anything, I'm just going to count electrons and I'm going to keep filling out my shells. Okay, so I know that the first energy level only has S and it can only hold 2 electrons. So I'm going to start there with those two. And then I'm going to come up to 2S and fill it out. So that'd be 2 electrons on that one. 2P can hold 6. So now I'm just going to stop here and do a total count. I am at 2, 4, 8 total electrons. So I have to keep going, right? So I get to 24. So next up we have the 3S, and I fill that out. 2. I have the 3P. I fill that out. 6. And if you're confused about what's going on, go back to your periodic table, right? I'm on row 3. That's principal energy level 3. And there are no D's here. So I'm not doing anything with the D yet. After I get through with 3S2, right, I go straight back to the P's over here on this right side. When I click off, I can't. Aluminum. Okay, so I'm at aluminum now, and I'm going to add all 6 of those electrons for that P orbital there. So that's where I'm at, 3P. Now I go to the next row. I start with 4S. Let me write that on there. 4S, 2. Okay, let's do a count real quick and see where we're at. 2, 4. 4 plus 6 is 10. 10 plus 2 will be 12. Plus 6, 18. Plus 2, that's 20. I'm at 20, so I'm getting close to chromium. And let's see where I'm at on the periodic table. So now I'm in this D region. Remember I said the D region is always one number lower than the S region for that same line. So when I write this in, it's going to be 3D4. 4 because I only have to do 1, 2, 3. Oh, y'all can't see my little arrow thing. Hold on. 1, 2, 3, 4 electrons from the D orbital. All right. So when I go write that in on my paint program, it'll be 3D4. Okay. Now, if I were filling in my boxes, this is an interesting point. Remember, D can only have 5 orbitals. So each box represents 1 orbital, and each box can hold 2 electrons. So if I were going to put in 4 electrons for my D orbitals, remember you go one at a time, all facing the same direction. That would be the orbital diagram for 3D4, right? All of these other ones are filled in. Say this is a box for 4S, the 4S orbital. Since that one have both electrons, it's filled in both up and down. Okay, and the same for all the 3Ps. 3P, make sure y'all can still see that. It gets cut off a little bit. Let me come over here. 3P has 3 orbitals because P can hold 6 electrons, each orbital 2 electrons, right? And then all of these are filled in with up and down arrows. Okay, so you go through, you put all the arrows up the first time, and then as you add more, you start from the left and put them going the opposite direction. All right, so I think that gets us through that part. Let's go back to the PowerPoint, maybe the text, and see what else is on there. Valence electrons. Okay, so now this is kind of the nuts and bolts of electron configuration. All of this is, we use it to kind of identify electrons, but when we start talking about reactions, you want to focus on valence electrons. So what a valence electron, what a valence electron is, let me see, are the electrons on the outermost shell. So I should have saved that little drawing I had of my atom. Let me see if I can pull up a good image real quick. Valence shell electrons images. This one looks good. So the outermost shell that we've been talking about, how the electrons fill up on these little shells, the outermost one is called the valence electron shell. All right, and those are the ones that get reacted with because those are the ones on the outside of the atom, right? We said that everything kind of forms this cloud. Well, the valences, depending on how many they are, will form a cloud on the outside that is slightly penetrable, right? It's like kind of like the fan. I can get my hand in there, but I can only get it in so far before something bangs it. So that's what happens on this outer shell. We have valence electrons that are moving round and round, but that's where the reactions occur. That's where I can get something in or take something out and make something happen, is on this outer electron shell. So that's why it's so important that we understand how many valence electrons are there and what the trends are when you're dealing with those. Okay? So most atoms like to follow what we call the octet rule. All right? The octet rule just means that no atom, or excuse me, every atom would like to have 8 valence electrons. Okay? So let me draw another little atom here. That's my nucleus. Okay, and then I do a shell. Let's do another shell and another shell. Okay, so the electrons on this outermost shell are going to be the ones that I would call the valence electrons. And in order to know how many that is, all you really have to do is look at your periodic table. Okay, so let me pull back up the periodic table. Whatever group number it is, that's how many valence electrons it has. Okay, and why is that? Because when you're filling out your electron configuration, that's the outermost shell is the one that's furthest down on the periodic table. So say I stopped here at sodium. This would be a 3s1 would be the last configuration that I drew. So that means this last shell, this 3s shell, oh, I can't get on there. Let's say this shell is a 3s1. That last shell only has one valence electron. One electron on the outermost shell will be one valence electron. So that's how come you can look at the periodic table and just say, what group is it in? That's how many valence electrons I have. For that chromium that we drew, we had 4 electrons. We had, well, excuse me, 6 electrons on that outermost shell because we had 2 from the S and then 4 from the D. So technically it would just be 4 on the outermost shell. But sometimes you have to count the S and the P's together. If they have the same number, they get counted together, right? Like 4S and 4P, both of those get counted as energy level 4. So pay attention to that number. That'll kind of tell you how many valence electrons. But the easiest way to do it, because we typically don't worry about these middle transition metals, is to just look at the group number. So 1 group group hydrogen, all have 1 valence electron. When you get to 2, group 2 all has 2 valence electrons. Coming over here to the right, like the noble gases, they all have 8 valence electrons. Okay, that gets me to the next kind of rule, if you will. Atoms would like to have either 0 valence electrons or 8 valence electrons. We call it the octet rule. Where's the PowerPoint? I don't see it mention anything about it. It's called the octet rule, and it says that the valence electron shell would like to have 8 electrons. It either wants 0 or 8, and depending on which side of the periodic table you're on, you can get there easily going one way or the other. So, for example, stuff on this right side, fluorine. Make sure y'all can still see me and I'm not on paint. Okay. Fluorine is in group 7, has 7 valence electrons. I think this might actually indicate how many valence electrons right there. But 7 valence electrons. Remember I said it wants to have 8? So the easiest thing for fluorine to do to get to 8 is to pick up 1 electron. And so you'll see it do that a lot of times. All right. Now picking up 1 electron doesn't change it into neon. It changes into a fluoride ion. And what an ion just means is it has 1 more electron than it should. Right? I have added an electron to this outer level here, and I have made it an octet. So now it has 8 electrons on that outer shell. This 3s is no longer applicable, so let me cut that out. I've added an electron to this outer shell, and it's made 8 electrons, but fluorine is only has what, 7, should only have 7 valence electrons. So that extra electron makes this fluorine negative. Remember we did the positive negative. If I have more electrons, it becomes more negative. If I have more protons, it becomes more positive. So you have to kind of keep track of how many electrons it should have and how many it actually has. Okay, let's do another one. Let's do that carbon. It's atomic number 6, but it's only got 4 valence electrons. Okay, so I'm going to draw this one, and I'm going to skip. Actually, I'll leave that. So this would be the outermost shell, and that is the 2p. I'll put right here is the 2s. This is 1s. Okay, so everything in the 2, let me draw an arrow to this one. This one is 2s, 2. And then the p is 2 electrons. Okay, now one of those things I was saying, the concept might be a little hard. Both of these energy shells right here are part of the second energy level. They're split up into subshells, but they would all be the valence electron. Okay, so both of these are the outermost shell, and the 2p's electrons are the ones that I'm kind of focused on to figure out how many I need to add or subtract. Okay, so I can do a couple things. If I take off 2 electrons, I'm still at the second energy level, so that doesn't really help me. Alright, so the easiest thing to do would be to add electrons in. So let me do that. Let me get that off of there. Let me add electrons onto the P. Okay? Remember we said that P can hold 6, so that's 4, 5, 6. Alright. Now I have 4 more electrons than I did as a neutral carbon. So this carbon would be a -4 carbon. Okay, remember if I add electrons, I'm going more negative in charge. So that is a -4 carbon because I've added all those electrons on there. I've added those 4 electrons, but if you look at my periodic table, you'll see why I did that. I was trying to get all the way over here to neon again. Just like we did with the fluorine, I added 1 electron to get to the neon configuration. With carbon, I had to have 1, 2, 3, 4 electrons to get over there to neon. Alright, so that's most of chemistry, is just trying to get to that 8 electron valence shell, or 0. If I'm on this left side, I might give up electrons, and that's when you see atoms become more positive. Mg, magnesium, will give up 2 electrons to get to 0, and then it becomes Mg2 plus. Okay, so we'll do some more work with that. I just wanted to kind of go over it lightly. This is a tough section, so put in the work, put in the practice, and try to get better at these little things. Okay. So, before we move on to periodic table trends, I want to kind of look at Lewis dot structures. Lewis dot structures are essentially just ways of writing the atom out based on the number of valence electrons. Okay, so let's go over some rules here on how to do that. Cut all this. Cut. Okay, back to drawing. Let's start with, we just did carbon, right? We said carbon had 4 valence electrons. So when you're doing a Lewis dot diagram, we call this a Lewis dot structure. You want to start, doesn't really matter where you start, but you want to go clockwise, and just how you filled in those orbitals 1 electron at a time, you want to fill in these 1 at a time. So 1, 2, 3, 4. Okay, and most all will be in this orientation because of the octet rule, right? So if you imagine each one of these holds 2 electrons, and each one of these is one of those orbitals that we were talking about, then you'll see that 4 times 2 equals 8, right? Now let's add in those 4 electrons like we did on that last problem. That's how you'll add them in. So clockwise, I didn't really do it there, but clockwise 1 at a time. Once you get all the way back around, that's when you start going to 2. All right, and your goal is to get to 8 valence electrons. If an atom does not have 8 valence electrons, that means it's trying to do something else. It's going to try to react with something. It's going to try to give up electrons, or it's going to try to gain electrons, whatever way that it can, so that it gets to this octet rule, 8 valence electrons. All right, and there are exceptions. We won't talk about that just yet because it can get confusing. If I see one in the PowerPoint or whatever, I will address it though. So let me go back to here. And so you'll see that they did exactly the same thing. So chlorine has 7 valence electrons. They started right here, I guess, and said 1, 2, 3, 4, 5, 6, 7, right? And left that lone electron on the right over there. Let me see what else it talks about as far as the electron dot. There's also connecting them. For example, chlorine. So let's take 2 chlorine atoms that both have, don't do that, that both have 7 valence electrons. So, like I said, in clockwork, 1, 2, 3, 4, 5, 6, 7. All right. Now I'm going to do another chlorine right below it, and I'm also going to put 7 there. 1. I'm not going to do the clockwork just because I know where I want this last dot to be. 3, 4, 5, 6, 7. All right. So chlorine, these 2 chlorine atoms are neutral right now because they have 7 valence electrons, and on the periodic table they are in group 7. And pull up the periodic table, chlorine right here, group 7. So it should have 7 valence electrons. That means that these chlorines are neutral. They don't have a charge as of yet. But if I added an electron there, it would make it chlorine minus, right? A chloride ion. So let's not do that. Same thing with the bottom one. Another option for sharing electrons is to make a bond, all right? And you'll start seeing chemical bonds in this class and kind of how you'll use them to your advantage to kind of do things, do little tricks like this. So I'm going to connect this electron with this electron. That's one line. Let me take that off. I'm going to connect this electron with this electron. And now you'll see that 1, 2, 3, 4, 5, 6, 7 is in this one. Chlorine. 1, 2, 3, 4, 5, 6, 7. So these bonds actually are 2 electrons, and that's a single bond. I didn't want to put that extra little line there. Let me erase those 7s. Alright, so this bond here is essentially sharing the electron. I took the 1 electron from the chlorine, the 7th electron, and I shared it with the one on the right. So that means that the one on the right now has 8 valence electrons. If I count this bond, it fills my octet. There's 8 valence electrons because 2 electrons are wrapped up in this bond. That's an E. 2 electrons are wrapped up in this bond right here. Same for the left side, right? I took the 6 electrons I have here as lone pairs, and then the 2 from the bond, and that makes a total of 8 valence electrons on that. So we can share electrons with each atoms. Atoms can share electrons with each other to make the octet, to fill their octet. Alright, so these are kind of the tricks that you'll use to find out how you pair. And if you actually look in nature, you'll see that chlorine often exists as a chlorine molecule, 2 chlorines connected just like this. Okay, and the reason that is because they like to fill that octet. And so everything in chemistry pretty much follows the similar patterns. Alright, just to take another quick look at one, let's do carbon for example. So remember when we did carbon, we wanted to add 4 electrons, but it made it a 4 negative carbon, and that's just not stable. It's a very high energy molecule and not likely to exist for long with it bumping into everything else. It's going to lose those electrons. It's not going to be able to hold on to them like it wants. So what carbon ends up doing, and one of the reasons it's the building blocks of life, is it connects something on every side just about. One way or another, it fills that octet all of the time. It might do it by hooking up with a hydrogen atom. So it's like say 4 hydrogen atoms, 1 on each side. And that will get the electron from the hydrogen shared with the carbon and make the octet. And so this ends up becoming CH4. Okay, let's look at oxygen for example. Oxygen and water. So oxygen has 6 valence electrons. It's in group 6. I'm going to put those on here. 1, 2, 3, 4, 5, 6. Alright. So notice that it has 2 single electrons, and it's 2 electrons away from filling its octet. So typically what oxygen will do, it will form 2 bonds. If it's water, it'll form a bond with hydrogen and share that electron with hydrogen. Right? And then that becomes H2O. And my octet is filled for the oxygen. Now hydrogen and helium can only have 2 electrons because they're in that first energy level. Right? Looking at the periodic table, see that hydrogen and helium are up top. They can only have 2 electrons. So their full electron cloud would be 2 electrons. And so that's why you see hydrogen, like we did on the carbon, it just donates 1 electron, and it's filled by having the 2, 1 from the oxygen and 1 from itself. That fills a hydrogen and a helium. But most other molecules want to have 8 octet. Okay, so that gets us to the Lewis dot structure. That is a Lewis dot structure, right? I've connected the hydrogens with a bond. There'll be some where you'll have to do double bonds and triple bonds. I haven't seen that yet on this chapter, so I'm not going to get there yet. But just know that every bond holds 2 electrons. So if this were a double bond, let me think of one that has a double bond. cut. What has a double bond? H2CO. Let's do that. So sometimes what oxygen will do is put both those, instead of doing two single bonds like this, it'll put both the electrons in a double bond. Okay, so this is what we call a double bond. Let me do another one on this side. Valence electrons, 1, 2, 1, 2. Okay, so now I'm going to go through and I'm going to count all the electrons associated with each atom. Okay, so the oxygen has 4 in lone pairs, right? 2 here, that makes 4, but it has 4 electrons locked up in this double bond. Okay, 2 for each line. So that's actually 8 electrons around an oxygen. Okay, let's look at the carbon. The carbon has 2 electrons in this bond, 2 electrons in that bond, 2 electrons in that bond, 2 electrons in that bond. So that's 8 total around the carbon as well. Same for the other oxygen, 8 valence electrons around that. So you'll see how you can make these double bonds and create different molecules, but you still end up getting to the octet, the 8 valence shell electrons. Alright, so that's the Lewis dot diagrams. I'll put another video on there. You want to kind of play around with that. I'm not sure how much the program will ask you about it, but that'll definitely something that you will see on your midterm is Lewis dot structures, Lewis dot diagrams, and how to connect different atoms and why you would connect them. Okay, go back to the PowerPoint. We're getting close to finishing up. What's my time at? Almost an hour. Yeah. So I apologize. Like I said, some of this is tricky stuff, and it gets like the orbitals especially. That's kind of organic chemistry stuff, and I would rather cover that in the second portion of survey. All right, so now for periodic table trends, you just got to kind of remember these. You can do like a little diagram or print up. There's a bunch of examples on the internet. So let me do periodic table trends, periodic trends. Yeah, so any of these will work. Let me make sure y'all can still see what I'm saying. Yeah, any of these little kind of diagrams. But let's go over some of the reasoning behind why they move the way they do, why the trends go in the directions that they do. And most of it has to do with valence electrons. Okay, so going back here, let's look at, what do they talk about first? Atomic size. So atomic size decreases across a row, but increases as you go down. All right, so just doing like a little drawing. Let me kind of explain that. Wish I did have my iPad. This is getting to be a lot of drawing. Pen. Okay, so let's just do 2 different atoms from the periodic table. Let me find what they got. Carbon and nitrogen. So decreases across a row, but increases top down. So let me do a comparison with some that are on top of each other. So let's do beryllium, magnesium, and lithium. Okay. So lithium, magnesium, and beryllium. Okay, so this is the order that they're in on the periodic table. This one's number 3, 4, and this is like, what number is that? Oh, I did them backwards. Beryllium's 4, magnesium is 12. So it's beryllium, magnesium. Okay, so across to the right, so we're talking about atomic size right now. Let me undo that. Alright, so this first one is going to be lithium. The second one is going to be beryllium. As I add electrons, right, so this one only has one electron on the outer shell. This one here has two electrons on the outer shell, but it's the same shell. So these create forces, right? The electrons are negative, this nucleus is positive, so it creates this force that pulls into the center. So the more electrons I have on there, the more it's going to pull into that center and make it smaller and smaller and smaller. That's how come when you go from right to left, right, or excuse me, when you go from left to right on this periodic table, the atoms get smaller. So fluorine is smaller than oxygen. Oxygen is smaller than nitrogen. Nitrogen is smaller than carbon, so on and so forth. But when you're going up and down, oh, where's my paint? So say from beryllium to magnesium, you're actually adding energy levels, right? So if I'm drawing, let's see, this is beryllium here. Let's do magnesium here. Magnesium, roughly about the same size nucleus, right? But what it has is more energy levels. I've come down and I've added, looking at my periodic table, I've added a 2p shell and I've added the 3s shell. So it has two more shells than the beryllium did, thus it gets bigger. All right, as you go down, the atomic size is going to get bigger because I have more shells. I have more electron shells and it gets wider and wider. If I have more electrons on the same shell, they're going to be smaller because those electrons are pulling in so tight. All right, so that's atomic size. Let's look at ionization energy. So the ionization energy is essentially how close to the octet it is, right? How far away from the far right or the far left of the periodic table. Remember, if I'm on the far right, I have filled my octet. I have 8 valence electrons, and I am very happy to be there. Okay, if I'm not, if I'm fluorine or nitrogen, I have less than 8 valence electrons, and I'm going to do whatever possible to get to 8. All right, one of the things that I can do to do that is to make an ion, the ionization energy, and that's kind of what we're talking about here for the periodic table trends. Let me pull up PowerPoint and see what they say about it. The energy needed to remove an electron from a neutral atom. Okay, so ionization energy decreases down a column. All that means is that as the electrons are further away, right, as I get further and further out on these shells, it gets easier and easier to pluck an electron from there. So the ionization energy, the energy needed to pluck an electron, gets lower as I get further away from the nucleus. Okay, so top down, the trend is ionization energy gets lower. Now, from left to right, ionization energy gets, it can be a little more complicated because different ones can go different ways. So let me go back here and see if they show you. All right, so for example, the highest ionization energy is going to be the ones with the octet. They are going to require the most force to get that electron away because they were so happy holding those 8. Okay, and then it's just going to get slightly lower as you go from right to left. Okay, so fluorine will have a large ionization energy. Oxygen will have not quite as much ionization energy. It'll get easier to pull electrons as you get further away from the octet. So just remember that the octet is the max ionization energy. Everything coming left is a little bit lower. All right, that's the easiest way to think of ionization energy until you wrap your head around what valence electrons mean and what that does for the atoms themselves. Okay. It doesn't really go over any other trends. Let me take a look at the text and just make sure I'm not missing anything. Where is the text? Text. Periodic table trends. Yeah, that's really all it does is ionization and atomic size. But you'll see, like on the internet, when I looked it up, there were several other different metallic character, electron affinity. Electron affinity is really similar to ionization energy, so maybe that's why they didn't cover it that way. Um, and atomic radius. Yeah, I mean, you can look over some more of these. I will not ask anything that's not in the text. Electronegativity we'll talk about later. Um, but it pretty much peaks at fluorine and oxygen, and then everything else is lower in electronegativity. And that's just how much it likes to hold electrical charge, how much it wants electrons. So very similar to ionization energy as well. And I think that's all I'm going to do today. So just, I said, tough chapter here. Electron configuration is really the nuts and bolts of why reactions happen. So understanding that will give you a good leg up on doing some of those reactions in the future. It's also very useful determining charge, right? We talked about having more protons or electrons can create positive and negative charges respectively. So understanding valence electrons and electronic structure are key to kind of understanding what that normal charge of an ion would be. Fluorine, as we said, likes to take that electron up. It likes to be fluorine minus, okay, and become a fluoride ion. Um, when it's neutral, it's paired up with something. It gets that electron from another atom instead of, empty space, pulling an electron out of wherever, air or electricity is electrons. So there's different ways that they can get those electrons. Um, but most often it's in through a bond or a pairing of some type. So that ought to get you to chapter 3 for Alex. So let me know if you run into any problems. I know this was kind of a long lecture. I'm trying to catch back up and get ahead also. So I want to make sure that I cover things that you're going to see in the future and that I'm not missing anything that you're going to be tested over. Okay, so if you run into any trouble, like I said, email me. And I've extended a lot of the due dates on Alex. If for some reason you're locked out, contact me and I can look at an extension or what went wrong, whatever. All right, so that's it for chapter 2. I'll see y'all next time. Bye.